Alright, hello there. This is Professor Jesica Abrams at Broward College, 2086 BSC Lab, which is Anatomy 2, and we are talking about the exercise number 29, functions of the heart and the blood vessels. So this will be our last exercise on the cardiovascular system, and now we're going to talk a little bit more about its electrical functions. So what is a cardiac cycle? Well, the cardiac cycle is all of the events that occur in one heartbeat. And this is going to include 2 rounds of something called systole and 2 rounds of something called diastole. So the function of the heart obviously is to pump blood throughout the body, and it does this by pumping, which means to squeeze and then relax. Squeeze, relax, squeeze, relax. So the process by which it's contracting or squeezing is going to be systole, and then the process by which it's going to relax is called diastole. And keep in mind that diastole, or relaxation, is just as important, if not more so, than the actual contraction phase. Because if you can't relax, then you're not going to have any energy to keep going with your contractions. So atrial systole is one of the systoles when we talk about that there's 2 per cardiac cycle, and that's going to be followed by ventricular systole or contraction of the ventricles, and then you have atrial diastole, which is the rest, followed by ventricular diastole. So your heart is made up of about 99% or the vast majority of contractile cardiocytes, which means they have the ability to contract and relax, but they have to be told to do so. And then you have this small number of cells that are autorhythmic. In other words, they themselves, auto means self, right? So they themselves set the rhythm. They're able to spontaneously decide that this is when they're going to contract. So the pacemaker of the heart is the boss of sending the impulses for the rest of the cells to contract, and it's going to be the origin of the signal. And it's called the SA node because it stands for sinoatrial, so it is in fact located in an atrium, and it's in the right atrium, which should make sense to you because if you remember back to the I'm a little blood drop, that's where everything starts and ends, right, is in the right atrium. So it's not only going to set the rate, so in other words, the number of times that it beats per minute, but it's also going to set the rhythm, right? So a funky rhythm when it comes to music is a good thing, but you want a nice, solid, regular rhythm when it comes to your heartbeat. You don't want it going all over the place, fast and slow. And the SA node signals to stimulate atrial systole, so it's going to stimulate the contraction of the atrium first, and this is going to force blood into the ventricles, and if you remember, the blood goes out the aorta from the ventricles into the rest of the body. You also have something called an AV node, which is the atrioventricular node, and that one's located on the floor of the right atrium, right next to the ventricle, and that's the gateway to the ventricles. So this one's actually autorhythmic too, and it's able to, gosh forbid that your SA node malfunctions, it's able to regulate rhythm, but not for an extended period of time. You really need your SA node in full force to have a regular heartbeat to stay healthy. And in fact, this is the artificial, when somebody talks about a pacemaker, they had a pacemaker put in, it's because there was something wrong with their SA node. So they have an artificial SA node implanted that sets the rhythm and the rate of the heartbeat so that it can continue to function normally. So after this signal is transmitted from the SA node to the AV node, if everything's functioning properly, it then goes down the AV bundle of His, and the bundle of His extends through the interventricular septum, which if you remember is that the space that connects the 2 ventricles together. So you can imagine that's very important because that's the bulk mass of the heart. There's more space, more mass in the ventricles than there is in the atrium. So that's really going to start spreading it down. And then that's going to divide to the 2 sides of the heart into right and left bundle branches, and those emerge at the apex, which is that pointy part at the bottom of the heart. Remember, the base is at the top, the apex is at the bottom, in something called Purkinje fibers, of course named after somebody called Purkinje who discovered these. And those are going to go ahead and distribute that signal all throughout all of the contractile cardiocytes of the heart. So you've probably heard of EKGs before or seen one, and technically they should be called ECGs, at least in America, because it stands for electrocardiograph. So normal sinus rhythm, sometimes called NSR, sometimes just called sinus rhythm or sinus, means that your heart is beating regularly as it is supposed to. Any aberrant or abnormal rhythm would be called arrhythmia, because A means without, so without rhythm. The normal rate of heartbeats is about 60 to 100 per minute. The point that I made here was that if you have a heart rate of 55 or a heart rate of 110, does that necessarily mean there's something wrong? No, but this is the average number of beats that it should be per minute. And if you have less than that, we call it bradycardia. If you have more than that, we call it tachycardia. The machine itself that is able to detect, amplify, and record the electrical signals that are coming from the heart while it's beating is called an electrocardiograph. The strip that it produces that you're able to see is then called the electrocardiogram. And if you look at it, it contains deflections, which are those ups and downs like this, and intervals, which are the points that go straight across like that, both of which are important. So for the deflections and the intervals to make sense, you have to really think about what's happening within the heart. So how do cells talk to one another? Well, we said that intercalated discs were only found in cardiac muscle, and they were so important because it allowed the heart to beat synchronously. In other words, you don't want part of your heart beating and not the rest of it, right? Or part of your heart beating at a different rate or rhythm than the other parts of it. And intercalated discs are allowing the rapid conduction of impulses from one cell or cardiocyte to another. So cells at rest are polarized, and we call that resting polarization a resting membrane potential, and it's absolutely essential to their excitability. In other words, their ability to beat and be contracted. So what does polarized mean? Well, if you think of polar like poles, like the North and South Poles and where Santa lives, they're the extremes, right? It means that the ends are different. So if you look at this, you can see that there's a charge difference from one side to another. So that means that it's polarized. If there are more positive charges on one side or more negative charges on the other side, then the cell is going to be polar. If the two charges are equal, then it's not polar. So an influx of ions, in other words, if you let a bunch of charged things into the cell, then they're going to decrease that polarization. In other words, make it less polar because you're going towards equilibration. And as that's happening, we call that process depolarization, because D means without and polar is a difference. So it's going to have less of a difference. And you can see that from this lovely action potential. You thought you'd get to forget about that after Anatomy 1, I know, but not such luck. So you can see that the depolarization, it's going from this resting membrane potential. So normally the cell has more negative charges than the outside environment does. So the resting membrane potential is negative. It's about negative 90 in a heart cell. And then it's going to start depolarizing. So the cell is becoming less polar, which means it's becoming more close to zero. And as that's happening, you're going to see on the EKG in a minute here, or the ECG, that it's going to start to contract. And then, just as important as the depolarization is the repolarization. And why is the repolarization so important? So re means to go back to, right, to return, and polar means difference. So at this point you're becoming less different, less negative. At this point you're going back to being negative again. And in order for this to happen, which is going to correlate to the contraction, you need repolarization, right? You can't get less negative unless you're negative to begin with. So you go back to negative and then back to positive, back to negative, back to positive. And yes, you go a little bit above that which is needed, and you usually go a little below what's needed as well, but the point is that you have to get back and forth between these two states.